unfavorable to put a plus charge on the chlorine electronegative atom. It's also terribly, terribly unfavorable to separate these compounds in an ionic fashion. Indeed, we break this bond, and really quickly we generate full minus and full plus charge, and these things actually immediately recombine. So if we even think about this particular process, if we were to measure the energetics of it, it's actually very, very difficult to ionize chlorine-chlorine bond in such a way that we make a Cl minus and a Cl plus. Lots of reasons why it's difficult. They want to recombine. Chlorine definitely doesn't want a plus charge on it. So this particular process is kind of unfavorable, and for all intents and purposes, it doesn't happen. Okay, maybe we can be a little bit more brave here. It is a Wednesday morning after all. Let's just put X's here. This particular process does not happen is the theme that I want to kind of impress upon you. The other possibility, one that actually works, as you already know from watching the video, is known as homolytic cleavage. Homolytic cleavage means even bond breaking, and there's many possible ways for us to do this, but the key thing is we're going to use a single fishhook arrow. Now, we're going to imagine breaking this bond evenly this time. Just imagine chopping it in half cutting it in half with a knife or chopping it with scissors. We're going to give one electron to one chlorine and one electron to the other. And the single fishhook arrow, now it's very important we don't confuse it with a double. This means moving one electron. And in this case, this means breaking this bond, giving one of its electrons to this chlorine, breaking this bond, giving one of its electrons to this chlorine. This is also an equilibrium process. We make two very reactive species. And these species are called radicals. Any atom with a single unpaired electron can be called a radical. In our particular class, we're not going to use a dot for this. I want us to use a star when we have an unpaired electron like this. It doesn't have to be a 5-pointed star, a 6-pointed star, 7-pointed star, 10-pointed star, but we're going to use a nice big star for this. We're not going to use little dots anymore for these types of things. This is going to keep in mind that we have to do something with this electron. It's going to keep us in mind that this is a special entity. It's going to keep in mind that this unpaired electron makes this very, very reactive. So any species, I'm not writing everything down, but some of these things you might want to write down. Any species that has an unpaired electron is called a radical. These species are reactive. They want to satisfy the octet rule, and chlorine here is neutral, has 7 electrons, but it's in violation of the octet rule. So it's going to somehow want to get back to the octet rule and obtain electrons from somewhere else. So this basically describes why radicals form. There's 2 choices here. Heterolytic cleavage is energetically unfavorable. This process is favorable, can happen as soon as we give chlorine about 250 degrees of energy. We're now going to talk about and go back to the reaction. I'm going to switch the paper to kind of a vertical mode here. Maybe this will work a little bit better for this. But we're going to revisit this basic reaction. This is going to be called the monochlorination of methane, or the reaction of chlorine, Cl2, and methane. And this process, as the pre-lecture video described, has many complex steps in it, and I really glossed over them quickly. Didn't want you to worry about them because I wanted to spend our time together today working on these things. They're complex, they're new, they're going to take time to digest, and we do so by writing and drawing and practicing these things. There's 3 steps that happen in this particular reaction. We're going to go through them one at a time. The first step we're going to formally call the initiation step. The initiation step is the one that gets this reaction started, and it's the one we were just looking at on the previous page. The initiation step takes our halogen, and when we heat this thing, or shine UV light on it, the bond will break. It breaks homolytically, the most stable or most low energy pathway. The heterolytic process is very high energy, doesn't happen. And when this happens, the bond breaks, and we make 2 chlorine radicals. When this particular process happens, it's kind of interesting. The distance between these 2 atoms is some value d. We can look it up. We're not going to. But when we first shine heat or we shine heat or heat with UV. No, we shine UV light or heat it up, bond breaks, and what happens here is that the distance between the 2 atoms doesn't change. So first particular step that happens, we just break the bond, but the distance is the same. We've just made 2 very, very reactive species right next to one another. Chlorine 1 wants an electron. Chlorine 2 wants an electron. They're the same distance apart, and the majority of the time, what happens is that these 2 species recombine. The 2 electrons get pushed right back towards one another, and the reaction goes in reverse. So usually, reverse reaction takes place. It's very strange. What are we doing, Dr. Schramm? We're just making something just to make the thing where we started from? Well, that's what really happens. So this is very reactive. They're in the same distance. They both want the thing that the other one has. They want to share, be friends, and make a covalent bond. And usually that happens. But this particular reaction, here's a key point. Once in a while, a radical escapes. That's literally the language we want to think about. Most of the time the reverse thing happens, but once in a while, a chlorine radical vibrates loose, goes off, and then does something different. Okay? These are going to be called propagation steps. So only very rarely does a radical escape. Okay? When that radical escapes, it starts hunting for electrons. So this radical has escaped this is actually called a cage. We don't need to worry about that particular language right now. But once in a while, radical escapes. We're going to redraw it, and then we're going to draw whatever alkane we were working with. Luckily for us, we're going to use methane, the simplest possible alkane that I can imagine. So chlorine leaves the cage, escapes, and it goes out and it's in need of an electron. And it bumps into a methane molecule. Methane molecule, or the other thing there's a lot of in this reaction. And so this thing wants 1 electron. That's the key bit. It doesn't want 2 electrons, it wants 1 electron. And the place that it's going to get it from is this bond right here. Methane has lots of electrons. Chlorine radical wants some of them. It comes along and it wants 1 electron. It's going to get it from this bond, and we're going to leave behind 1 electron on carbon. Notice again that this arrow means moving 1 electron. This arrow means moving 1 electron. So, chlorine wants 1 electron, conveniently bumps into a methane molecule, very rudely steals an electron along with a proton from it. And we can see from this series of reactions, steps, means this bond is going to break, 1 electron is going to go to carbon, 1 electron is going to go to chlorine, and this hydrogen atom is going to migrate right along with the electron to make a bond. And so what we make here is HCl. And I want you to very carefully draw how many electrons you think are on carbon, what's the formal charge on carbon, based on our very introductory knowledge of this process I did with 2 red arrows here, right? You can see where this bond came from. One of the electrons came from hydrogen-carbon bond. The other one was the radical. Now we're back to a covalent bond. So one of those electrons went here. The other electron, this arrow shows it going to carbon, stays right there, okay? And now we've made an alkyl radical. It's from an alkyl group, but specifically in this case, we've made a methyl radical. The specific name is methyl radical because it's a methyl group, but the general name is alkyl. If we did this with ethane, propane, butane, we'd have an alkyl radical. Okay. We learned that the hybridization of carbon in this is sp2 hybridized in our last class. We probably won't spend too much time on revisiting that. It's not the most important thing for us, but the hybridization of carbon changes a little bit. It goes from sp3, when we're bonded to 4 things. Here we're bonded to 3 things plus 1 electron, and the geometry changes. It becomes flat, trigonal planar. We have a p orbital with 1 electron in it. We may or may not elaborate on this in this fast-paced summer course. It's not really essential to redraw these things for right now. So we still haven't made our product yet. Instead, what we've done is we've transferred our problem child from chlorine radical. Now we have a methyl radical. Okay, all we're going to do, we're never going to panic, all we're going to do is we're going to redraw the radical in the next step. The propagation steps have 2 components to them. The initiation step has 1, it's very simple. But the propagation step starts when the chlorine radical finds its way to a methyl molecule. Valence electron gets 1, and it leaves the problem now with the methyl group. We now have a methyl radical. Here's the very, very important point about the second propagation step. There are very, very, very few chlorine radicals ever produced in this reaction. There are very, very few methyl radicals ever produced in this reaction. When we first make a chlorine radical, and it leaves the cage, we only have a little bit of it. It reacts with a methyl group. It makes a tiny, tiny amount of this methyl radical. This methyl radical wants electrons, and the place it is going to get them from is Cl2. It doesn't get them from Cl radical. There's not a lot of it. There's not a lot of this. The probability of these 2 things finding each other is tiny. This is very reactive. This is very reactive. These species are short-lived. They don't live very long. They're never going to find one another in any practical sense. Instead, the methyl radical finds a chlorine molecule. What does the methyl radical want? Well, it wants an electron. Chlorine has a weak bond, we saw previously, and we can give it 1 electron, break this bond, give that other electron to the other chlorine, and I want you to draw, we're going to go a little crooked here, on my notes anyway. I want you to draw the 2 things that you think emerge from this particular 1 electron process, 1 electron process. Again, bond's going to break homolytically. This only needs 1 electron. Let's give it 1 electron from this bond. Let's give it the chlorine atom. The other chlorine atom is going to separate off with 1 electron. Please try to draw what you think the C and D parts are for this particular reaction.